Suppose that I have a voltage source. Can be any kind of voltage source, and I represent it by a Thevenin equivalent circuit. So then I will have basically something like this with a voltage and a resistance. And now I connect my arbitrary source to an inductor. So I create this circuit that I'm drawing now. So I connect it to an inductor. And I ask the question, what's going to be the current that will flow around this loop? And what will be the current that flows basically after a long period of time? So I'm asking about what's called the steady state behavior. So after some initial transient has taken place, what will be the current that flows in this circuit? Well, we can analyze the voltage across this inductor, and we can analyze the circuit using Kirchhoff's voltage law. So KVL is going to give us the following. So starting at the bottom left corner, I'll have a negative due to the voltage source, plus R times I. I'll write that as R Thevenin to match my diagram. So R Thevenin times I plus VL is equal to 0. Now what can we do with VL? Well, we know from the definition of an inductor that the voltage is L times di dt. However, we're asking about steady state. However, at steady state, all time derivatives are 0. Right? Steady state means nothing is changing. If nothing is changing, any derivative with respect to time would be 0. So therefore, di dt is equal to 0. Therefore, VL is equal to 0. So if you have 0 volts across a circuit element, that circuit element is a short, right? VL equals 0 means the inductor behaves like a short circuit. So we can redraw the steady state DC circuit as, and we just had our voltage source, which we represent as a Thevenin equivalent circuit. And then we said that ran through an inductor, but the inductor behaves like a short circuit. So that's all we have. Voltage source just connected directly through the short circuit. So our important rule that we need to remember, so under steady state conditions, inductors behave like short circuits. And this rule you need to remember. Under steady state conditions, inductors behave like short circuits. If you forget that, go back and think about the definition of an inductor. Voltage is L di dt. Steady state means time derivatives are 0, and you'll get there pretty quickly on your own. Let's have a look at capacitors. What happens for capacitors? What about capacitors? So let's do the same thing as before. We have voltage source, which we represent with Thevenin equivalent circuit. So this is true for any linear source, any linear circuit. And we connect a capacitor into that. And again, we ask the question, what will be the current that flows in this loop? Well, let's analyze it. Kirchhoff's voltage law will give us the following. I should label on here a voltage across the capacitor plus VC is equal to 0. Now, what do we know about capacitors? Well, we know that in capacitors that the current is C times dV dt, but we're talking about steady state. So at steady state, all time derivatives are 0, so dV dt is equal to 0. Therefore, the current in the capacitor is equal to 0. So what will actually go on in this particular circuit? Well, there's no current that can flow. No current means open circuit. So a capacitor, under steady state conditions, behaves like an open circuit. So we can actually go back and have a look at our analysis based on KVL. KVL is still going to apply here. From equation 1, if we substitute in I equals 0, then we basically get that the voltage, Thevenin voltage, plus the voltage on the capacitor is equal to 0. The second term here cancels because there's 0 current, which is basically saying that the voltage on the capacitor is equal to that Thevenin voltage, and there's no current flowing. So the capacitor is fully charged up to the voltage of the power supply, e.g. the capacitor is fully charged to the voltage on the supply. So we can redraw the circuit as we have our source. We have the resistors there, but it will have no impact because there's no current flowing. And we had basically this kind of open circuit conditions where there's a particular voltage appearing across those terminals, but no current will flow. So most importantly here, I equals 0. There is no current that will flow through that capacitor. So our important rule is that the steady state DC direct current, steady state DC behavior of a capacitor is an open circuit. In other words, no current. Current equals 0. And this one is an important rule that you need to learn. Again, if you don't remember this, you could go back to the definition of a capacitor and you could say, well, steady state means time derivatives are 0, dV dt 0 means 0 current means open circuit. So you'd get there pretty quickly on your own. Let's recap. So for inductors, under steady state conditions, they behave like short circuits. Capacitors, under steady state conditions, they behave like open circuits. And these are important facts that you need to know.